My name is Helmut Seidl. In this talk, I'd like to present results which I have obtained together with Müller on first-order transition systems. Consider, for example, a conference management system where you would like to specify the behavior in a way which is independent of the concrete set of participating PC members and the concrete set of papers which have been submitted. A convenient way to do so is to use predicates and updates to predicates by means of formulas from first-order predicate logic. In the first step of the conference management, for example, a predicate conflict is defined, while the second step provides a predicate assign, specifying how papers are assigned to PC members. Please note that each definition of a predicate may refer to predicates which have already been defined, but it may also refer to input provided from the outside world. This input from the outside world here is formalized by means of input predicates, in this case A1 and A2. Subsequently, repeatedly predicates report and discuss may be defined, which specify the way how the discussion goes on each paper, where eventually a predicate accept is defined, in this case in such a way that a paper can only be accepted if it has been discussed before. In this way, a first-order transition system can be viewed as the specification of a parametric system. A concrete instance of such a parametric system is obtained by providing a universe. In the case of a conference management system, this concrete universe provides a concrete set of PC members as well as concrete papers which have been submitted. Relative to such a universe, then, a state attained during execution of the transition system consists of a first-order structure. A first-order structure provides an interpretation for the predicates occurring in the specification. This interpretation is then an appropriate relation over elements in the universe. And the state transition incurs then updates to the relations in the first-order structures according to the first-order formulas provided in the specification. Now assume that we are given an initial hypothesis. This is a first-order formula which describes the set of all first-order structures which are admissible at the initial point of the transition system. The goal then is to verify that a specific invariant holds. Such an invariant consists of first-order formulas assigned to each of the nodes in the transition system, which provide us with which give a specification of all structures which possibly should arrive at when reaching that particular program point. Now, in order to verify such a given invariant, we may refer to the weakest precondition semantics of the transition system. This weakest precondition semantics is given as a series of strengthenings of the given invariant phi. So that the H strengthening provides specifications of first-order structures, so that for at least H steps the invariant cannot be violated. Given this series of repeated strengthenings, then the formula, the invariant phi holds at each program point u if and only if for each iterate h the initial hypothesis implies the value of the hth iterate at the start point of the transition system. This iteration here is defined in terms of the weakest precondition of a weakest precondition operator. Now consider a post condition phi and an update to some predicate except, then the weakest precondition operator with respect to S of the postcondition phi is obtained as follows. First, the right-hand side of the assignment to accept is substituted for all occurrences of accept, but that's not quite enough, because in the right-hand side of accept there could be input predicates like this, occurrences of input predicates like this A5 here. Now the weakest precondition should take into account every possible value with which this input predicate might have. So therefore a universal quantification must be added over all input predicates occurring in the update formula. So this iteration is nice, but in order to arrive at a practical algorithm, various issues must be resolved. So the first point is that during the iteration, more and more first-order variables may be introduced, resulting in a fixed-point iteration which need not necessarily terminate. Furthermore, it is not only the sheer number of variables, but also the quantifiers may alternate in an arbitrarily often, implying that the resulting formulas may fall outside any decidable fragment. And even worse, if formulas become too complicated, then universal second-order quantification may no longer be possible, implying that we furthermore fall outside the realm of first-order predicate logic. In order to deal with these issues, I'd like to mention two interesting approaches. So first, let me briefly sketch the Ivy approach. Ivy is a tool provided by Pardon-Sagif and various co-workers, and their idea is to restrict the logic to a decidable fragment, then and then not to perform, at least in the vanilla version, not to perform any fixed point iteration, but just guess first order formulas psi in the nice fragment, and then check whether a series of verification conditions is met. These verification conditions consist of that the initial hypothesis implies the value assigned, the formula assigned to the start node of the transition system, then that for every edge, control flow edge of the transition system, the formula assigned to the start point implies the weakest precondition concerning with respect to the operation at the control flow edge of the condition, the formula assigned to the endpoint of the edge. Moreover, the guessed formulas psi should imply the desired invariant. Now this provides us then with a series of implications which then are fed into some theorem prover, in this case set 3 for verification. Now Christian and I, together with Eugen Salinescu, have tried another approach. So our idea was just to apply abstract interpretation. That means we perform the fixed point iteration, and whenever formulas get too complicated, we apply some kind of strengthening so that the resulting formulas are simpler and can be dealt with in an effective way. So now, so here, in order to give you a flavor how such abstractions may look like, consider an existential nested inside a universally quantified to a universally quantifier for the variable x. So in that case, we might replace the existential quantification by using scolemization with respect to some kind of Skolem function. So here we choose just a very specific Skolem function, for example, the trivial Skolem function, which returns the value of x. Alternatively, we could also use a Scholim function, which returns the value of some constant. Or we may take the disjunction of these two, and by that obtain a strengthened formula without existential quantification. There's also a way how we may remove certain universal quantifiers. So here, in order to remove the universal quantification over y, we may simply replace every literal where in which y occurs by false. But clearly these kind of abstractions are rather crude, and therefore the question is, are there exist non-trivial classes of first-order transition systems where the issues with the fixed point iteration can be resolved without resorting to any form of abstraction? And so let us first have a brief glimpse at second-order quantifier elimination. So consider this formula f or a of x or not a of y. And we would like to remove the universal quantification over a. Then it turns out that this formula in fact is equivalent to f or x and y. So this means this idea can be generalized, resulting in the well-known observation that universal second-order quantification can be eliminated from all quantifier-free formulas or all formulas with universal quantifiers only. Universal first-order quantifiers only. But this is not the only class of first-order formulas where second-order universal quantifier elimination is possible. So there's, for example, this. Consider, for example, that formula to the left at the bottom. So there is an existential quantification over a variable z. Still, second-order quantification over a is possible and the equivalent formula without second-order quantification over a is shown here to the right. Again, not an equality between variables introduced, but even more interestingly, the existential quantification over z has disappeared. And this observation we would like to exploit to construct a class of first-order transition systems where not only existential quantification may disappear, but also second-order quantification is always possible. So the class of first-order transition systems which we introduced, we have called guarded and stratified. So consider the following assignment to the predicate except. The right-hand side has existentially quantified variables of all variables, existentially quantification over all variables which do not occur on the left-hand side of the assignment. Moreover, these existentially quantified variables are guarded, that is, they occur inside an input predicate, into a literal for an input predicate. And this kind of assignment we call, for that reason we call that assignment strictly guarded, but it is, moreover, we call it a reset because the predicate on the left-hand side does not occur on the right-hand side. And moreover, there is a stratification, so that is a mapping from predicates to numbers, such that the numbers of all predicates occurring on the right-hand side are less than the value of the predicate on the left-hand side. Additionally, we allow another form of assignments in our first-order transition system, which is shown here. So in this case, a formula of the right-hand side of the type we have seen on the last slide occurs here, but it is not used for defining the predicate on the left-hand side, but for increasing the value of the predicate on the left-hand side. So this kind of addition to a predicate we will call a strictly guarded update. And then the theorem which we obtain is that if we have a first-order transition system which is stratified and has strictly guarded updates and resets, then the fixed point iteration for a given invariant of universal first-order formulas only will terminate. And this implies that if the initial hypothesis H is also in a nice fragment, namely a Bernet-Schönfinkel formula, then whether or not the given invariant holds is decidable. There are variants of these theorems which we also take proof, and that is when we use more liberal notions of what it means for updates to be guarded, and perhaps also more liberal notions of what it means for it to be a reset. And so in particular, in the case that we have updates which are only guarded, then we still obtain that the fixed point iteration will terminate with universal formulas only. But in this case, we may not use any kinds of resets at the same time. Altogether, also for this class of first-order transition systems, we find that for all initial hypotheses in the class Bernet-Schönfinkel, that invariants consisting of universal first-order formulas are decidable. Now coming back to the conference management system, from the beginning, that system is strictly guarded and stratified. That means that in each iteration, second-order quantifier elimination is possible and resulting, which at the same time removes all existential first-order quantifiers. So, meaning that we always stick with universally quantified first-order formulas. Accordingly, implications to check whether the fixed point has been reached are decidable. Moreover, the number of universally quantified first-order formulas remains bounded, implying that fixed point iteration will eventually terminate with first-order universal formulas only. Okay, so this brings me already to the end of my presentation. We have identified a non-trivial class of first-order transition systems where safety properties, which are expressed by universal first-order formulas, are decidable. Now one may think of various generalizations of this kind of results. The first thing is, instead of safety properties, we may consider safety hyperproperties. Safety hyperproperties allow us to specify non-interference in multi-agent systems. And for this class, the same kind of for this kind of hyperproperties, the same kind of argument may be applied, resulting also there in classes of first-order transition systems where non-interference is decidable. Another interesting extension which might be considered is when going from transition systems to games, in order to go from verification to synthesis. So our goal would be there, given an objective invariant, an objective safety invariant as our objective, can we synthesize certain predicates in such a way that the resulting transition system satisfies the invariant. And it's not yet clear how we could the given class of transition systems could be extended in such a way that such a synthesis problem is effectively solvable.